Hi everyone, and welcome back to physics. This is Mrs. Hutchinson, and today we're going to continue our discussion with motion, and we're really going to get into the big five equations, the equations of motion, the ones that we're going to be dealing with quite a bit, and you have to really understand when to utilize each particular equation. So, when studying motion, like I said, there are five equations that are commonly used to help describe pieces of motion where some variables are known and at least one is unknown. For our purposes, we're only going to have one variable that's unknown because this is algebra-based physics, not calculus-based physics. Now, in physics circles or in physics communities, these equations are known as the big five equations of motion. And they're equations that you can find in your mechanics section of your reference table. And I'm going to show you where that is after we go over each equation. So equations that we already know. Velocity equals distance over time. Pretty simple one. We've already discussed that one. We've also discussed our constant acceleration equation, which is equal to change in velocity over time. Don't forget that this is equal to V final minus V initial over time. So let's say that we wanted to find the velocity, the final velocity of an object that experienced an acceleration. So let's solve this equation for final velocity minus Vi over t. So we will cross multiply. So in doing that, we would get AT equals VF minus VI. Add VI to both sides. And we would get VF equals VI plus AT, which is also an equation that's given to you in your mechanics section of your reference tables. If you don't have that out, you probably want it out for this particular video because we are going to be going over a lot of different equations. So your reference table also has this particular equation. Even though it's the same equation as our constant acceleration one above this, it's just solving for our final velocity. Taking a look at the distance an object moves while undergoing a constant acceleration. Basically, I'm not going to show you the algebra behind solving for this particular equation because there's a lot. So you're going to have to trust me on this, that we will get our distance or our displacement is equal to our initial velocity times time plus 1/2 our acceleration times time squared. And then last but not least, to get this final equation, there's a lot more algebra. A little more trust, but a lot more algebra, and we can solve for the final velocity of an object that experienced a constant acceleration over a known distance. So our variables that we would use here would be our final velocity, our initial velocity, and our acceleration and distance or displacement. There's another commonly useful equation, basically another commonly used equation for average velocity. This is one that you have used over years and years and years to solve for the average of something. The equation is only helpful if the acceleration is constant. And basically what you do is you'll take the average of the initial velocity and the final velocity. So you'll have your initial velocity plus your final velocity over 2. Please, please, please note that this equation is not in your reference tables. It's one that you're just going to have to know. It's only useful, major point here, if the acceleration is constant. If it is not constant, you cannot use this particular equation. Just something to be aware of. So here's the mechanics section of our particular reference table. You'll notice that the top 5 equations are the equations that we just discussed. We've got our average velocity equation. We've got our constant acceleration equation. We've got our equation that just rearranges our constant velocity equation. So these two are the same, they're just rearranged. We've got one that solves for displacement and one that solves for final velocity. Of course, you can use any of these equations that you find appropriate based upon the information or the variables that are given to you in the question. That is up for you to determine. They're not going to tell you, and I am not going to tell you, using this equation, you have to solve for this. No. What you have to be able to do is pull out the given information, identify what those variables are, identify what they want you to find, and figure out which equation or equations you are going to have to use to solve for the variable that they want. So let's go ahead and try an example. So again, let's do this. Here's our example problem. Starting from rest, let me get my red pen out. Starting from rest, a ball rolls down an incline at a constant acceleration of 2 meters per second squared. What is the velocity of the ball after 8.5 seconds? Okay, so we have a lot of information here. Again, this is why we solve, this is why we do our given. So let's write our given down first. Starting from rest means our initial velocity is 0 meters per second. Constant acceleration of 2 meters per second, so our acceleration is 2 meters per second squared. And what is the velocity of the ball after 8.5 seconds? So we have our time, 8.5 seconds. That's all of the given information that we have. They want us to solve for velocity. But here's the question. What velocity? We're starting from rest, we have our initial velocity. They're asking us, what's the velocity after 8.5 seconds? So they're asking us really about our final velocity. Granted, they didn't say in the question, what is the final velocity of the ball after 8.5 seconds? That's because you, as the reader, have to be able to pull that information out and understand that that's the final velocity. They're not always going to tell you that. So now, looking at our equations on our reference table, what equation deals with all of these variables? Our initial velocity, our acceleration, our time, and our final velocity. You could use one of two equations. You could use this equation. If I can write it a little neater, that would be nice. VI plus AT. There we go. Or you could use our acceleration equation. In my opinion, because they want us to solve for our final velocity, this one makes a little more sense to use. I would use that one, but it doesn't really matter, since they're the same equation, just rearranged. Let's substitute everything in with the units. So VF equals 0 meters per second plus 2 meters per second squared times 8.5 seconds. Let's solve for our answer. And we get our final velocity of 17 meters per second. So, pretty simple. Write down the given information and the wanted information. Figure out what equation is going to be useful in solving for that information. Substitute the values into our equation with our units and then calculate our answer. So we are going to be using the same process that we have been using from the beginning, but now again, this is why I wanted you to write your given, your wanted equation, substitution, and your answer, because it keeps everything nice and neat. So I'm going to help with example problem number 2. Let's go ahead and try this. So, reading the problem, it says example problem number 2. A cart rolling down a track has an initial velocity of 2.2 centimeters per second. Initial velocity. Begins to accelerate at a rate of 0.142 centimeters per second squared. How far has the cart traveled in 12 seconds? So how far? Okay. Let's write down our givens. What do we know? We know our initial velocity is equal to 2.2 centimeters per second. We know our acceleration is equal to 0.142 centimeters per second squared. And we know our time is 12 seconds. Wanted, how far has the cart traveled? So they're asking about our distance or our displacement. How far, our displacement. Let's figure out what equation we're going to use that incorporates all of these variables. We have our initial velocity, we've got our acceleration, we've got our time, and we want to solve for our displacement. So, looking at your reference tables, which equation incorporates all of those variables? We've got d equals VIT plus 1/2 AT squared. Now, why did I choose this equation? Because every single variable is given to us, and what we want happens to already be what we solve for. Now, that doesn't always necessarily happen, but if you look at the equation itself, we were given our initial velocity, we were given our acceleration, and our time, which makes things kind of nice. Substitution with units. So yes, this will be lengthy. So VI is 2.2 centimeters per second times 12 seconds plus 1/2 0.142 centimeters per second squared times 12 seconds. Don't forget to square our time. Please don't forget to square your time. Don't be that person. Please, please, please. So you substitute it in. You do a little algebra, you do a little calculamications, and you solve, and you get our displacement is 36.6. And what would our unit be here? If you take a look, centimeters. Bam. Okay, that's not so bad. Not terrible. I mean, it's not great, but it's not terrible. So now what I want you to do, yes, you guessed it, is pause the video, try question number 3. So try it on your own. Please write your given, your wanted, your equation, your substitution, and your answer. Please make sure that you follow that format. It does make a big difference. So one thing that I want to just make sure that you are aware of is that, for example, problem number 3, our units for that would be meters. I forgot to put them in. So an airplane starting from rest must achieve a velocity of 71 meters per second for takeoff. If the runway is 1 times 10 to the 3rd meters long, what must the acceleration be? So go ahead and use that information and solve for example problem number 3. Pause the video, and I will go over the answers when you're done. Hopefully you paused the video, so now I'm going to show you how to do this one. An airplane starting from rest must achieve a velocity of 71 meters per second for takeoff. If the runway is 1 times 10 to the third meters long, what must the acceleration be? So let's go ahead and write our givens. Starting from rest, that means that it's our initial velocity is 0 meters per second, because we're not moving to start with. Must achieve a velocity of 71 meters per second. So it says must achieve that velocity for takeoff. That's going to be our final velocity. If the runway is 1 times 10 to the third meters long, so our distance or displacement is 1.0 times 10 to the third meters, what must the acceleration be? Our wanted is acceleration. So, taking a look at our equations on our reference table, which equation incorporates all of these variables? We've got our initial velocity, final velocity, displacement, and our acceleration. We're going to use VF squared equals VI squared plus 2AD. You'll notice it incorporates all of the variables. Yes, we're solving for acceleration, and the equation hasn't solved for it, but we can do that algebraically. So now, let's substitute with our units. So we've got 71 meters per second squared equals 0 meters per second squared plus 2a is what we're solving for. D is 1 times 10 to the third meters. So we solve for this algebraically. Basically, this goes to 0. Divide both sides by 2,000. Times 1 times 10 to the third. 2 times 1 times 10 to the third. And solving for our acceleration, you should have been able to come up with 2.52 meters per second squared. Okay, not too bad. Again, it's just pulling the information out of the problem, writing down the given, writing down the wanted, and finding the appropriate equation to correspond with what's given to us. So now, yes, you guessed it. What I want you to do is pause the video and try the next question. One thing I want you to note is as these get more complicated, you will probably have to use more than one equation at a time. So just be aware of that. So pause the video, try question number 4, and I'll show you how to do it when you get back. Hopefully you paused the video and you've already completed question number 4, so let me go over this. An airplane starts from rest and undergoes a uniform acceleration of 3 times 3 meters per second squared for 30 seconds before leaving the ground. What is the displacement during the 30 seconds? Okay, so let's go over what's given. Airplane starts from rest. So VI equals 0 meters per second. Undergoes uniform acceleration. So A is 3.0 meters per second squared for 30 seconds. So we've got 30 seconds. The question is, what is the displacement? So, looking at all the variables, what equation are we going to use that incorporates all of those variables? Probably my most favorite one. D equals VIT plus 1/2 AT squared. Let's substitute everything in. Substitute with units. So we've got d equals 0 meters per second times 30 seconds plus 1/2 3 meters per second squared times 30 seconds squared. This is going to wind up going to 0 because anything times 0 is 0. Solving algebraically, we would get our distance or displacement is equal to 1350 meters. Not too shabby, right? So hopefully this made utilizing those 5 equations a little easier. And if you don't understand it, you can rewatch this particular video, and hopefully it'll be more clear as you watch it more and more times and as we practice it more and more. Hope you enjoyed it, and I'll see you for our next video.